In the last class, we have discussed angular momentum of a sliding block. Today, we are going to discuss angular momentum of a conical pendulum. First, I'll tell you what is a conical pendulum. You are familiar with simple pendulum. Your simple pendulum will be oscillating to and fro. Suppose you hold the simple pendulum and it is making a circular motion. You are rotating the simple pendulum. Just imagine you are rotating the simple pendulum with its bob moving in a circular motion. So that will represent a conical pendulum. That means the simple pendulum is tracing out a cone. That is how you represent a conical pendulum. So this is a conical pendulum. If you imagine this as the conical pendulum, it is rotating, the tip tracing out a circular path fixed at one end. That is drawn here. It is rotating about the z-axis. This is the radius of the circular path the conical pendulum is tracing out. This is the radius, and tangential to this circular path, the linear momentum P is acting, or the velocity is changing. Velocity V is acting tangential to this, tangential to the circle. That means it is perpendicular to the radius vector r or position vector r. So this is momentum P acting. So R and P are perpendicular in this case. Now we have to find out the angular momentum. We can find out angular momentum. I have considered two origins A and B. We'll be finding out angular momentum about the point A and angular momentum about the point B. Angular momentum is R cross P. This is vector R, this is P. Since these two are perpendicular, when you resolve the component of R, only the perpendicular component is considered, because the parallel component, the cross product becomes 0. So the magnitude of the angular momentum, LA is the angular momentum about the point A. So the magnitude of angular momentum at the point A, LA, is equal to magnitude of R perpendicular into magnitude of momentum P. That is equal to R into P. P is mv, the linear momentum. V is equal to r omega. So you can write angular momentum LA is equal to m r omega into r. That is m r square omega. And the direction of the angular momentum, because it is r cross p, it will be perpendicular to both r and p. R and p, if you look at the pendulum rotating like this, R and P are in the same plane. It is in the plane of the paper. So perpendicular to that is the direction of angular momentum A. So that will be along the z-axis. This is the z-axis I have drawn in the two-dimensional plane. If you look at the pendulum like this, it is along this line. So along positive z direction is the direction of the angular momentum A. So you can represent it by the unit vector k cap. So LA is equal to m r square omega k cap. And the magnitude of the angular momentum at the point A is remaining constant. Direction of angular momentum is also along positive z direction. So both magnitude and direction are not changing in the case of angular momentum about the point A. Now let us look at the origin B. I have taken the origin B and we are going to find out the angular momentum about the point B. The pendulum is rotating like this. If this is the point B, I've taken this as the point B, which is represented here. So this will be the length of the pendulum L, which I'm going to represent it as R dash or R prime. This is the length of the pendulum. Again, you look at the circular path. The velocity vector is changing in this direction. That means tangential to the circular path. So along that path is what momentum P is acting. It is rotating like this. Momentum is acting in this direction. So if you consider the plane representing this length L and the momentum, this is the plane R of plane of L and P, or R prime and P. Perpendicular to this is where Perpendicular to this will be the direction of the angular momentum, because this is the r prime, this is P. The direction perpendicular to this plane will be like this. So this is keeping on rotating. When the pendulum is rotating, the direction of angular momentum also keeps on changing. So angular momentum with respect to origin B, LB is equal to, this is the magnitude of angular momentum, this is magnitude of R prime, R dash is also called R prime cross P, which is equal to magnitude of R prime into magnitude of P. Magnitude of R prime is the length of the pendulum L into magnitude of P. P is mv, we have found out earlier, that is mr omega. You can substitute mr omega into L. So this is the magnitude of angular momentum at origin B. And the direction, I have showed you, it keeps on changing because the plane is rotating. Perpendicular to the plane of R and P, R dash and P, you have the angular momentum. So the direction of angular momentum with respect to origin B is not constant, and it is perpendicular to both R prime and P. Now coming to torque. You have studied torque in your plus 2 class. Torque tau is the rotating tendency of a force. Torque tau is represented by R cross F. So the magnitude of torque tau will be, again just like we have considered angular momentum, we can resolve R. Two vectors are there. Either I can resolve R perpendicular to F, or I can resolve F perpendicular to R. We have already discussed that. So in this case I have drawn R, this is the vector R, this is the force F, this is the same thing. Here I have resolved the position vector component perpendicular to F. Here I have represented force perpendicular to the position vector R. So both will be the same. So magnitude of torque is magnitude of R perpendicular into magnitude of force, or magnitude of R into magnitude of force perpendicular. So this again I can represent by the determinant form. Tau is equal to ijk xyz fx xy fz, resolving it into the xyz component. Here we have shown only the xy plane. Now coming to the sense of rotation and the direction of the torque. This also we have discussed earlier, clockwise, anti-clockwise rotation, but again I'll be telling you once more. Two masses m1 and m2 are there. m1 is having position vector r1, which is acted upon by a force f1. This force is acting in this direction. So it is tending to rotate the mass m1 in the anti-clockwise direction. So the direction of angular momentum will be along the z-axis, positive direction. You look at mass m2, position vector is r2, force f2 is acting in this direction, tending to rotate it in the clockwise direction. So the torque will be acting in the direction of the torque will be along the negative z direction. Torque on mass m1, tau I am taking 2-1, which is r1 cross f1, being anti-clockwise along the positive z direction, and torque on m2 being anti-clockwise, it is along the negative z direction. Now let us consider torque acting about the center of disc. Different cases, 3 different cases I have considered. This is a disc of radius r. A force is acting in this direction, diametrically opposite. Another force is acting in the opposite direction. You have studied couple, isn't it? Equal and opposite forces acting on a particle. The distance between these two forces is, this is r. So distance between these two forces is 2r. So the torque will be 2r into F. And the torque is 2r into F. Just look at the force acting on the center of the disc. Forces are equal and opposite. They will cancel off. So the total net force will be equal to 0, whereas torque will be 2rf. Now look at this case. This force is trying to rotate it in this direction. This is trying to rotate it in the opposite direction. So both will in effect cancel each other. So the torque will be 0 in this case, whereas the force you have F acting in this direction, again one more F acting in this direction. So they will add and the total force will be 2F. Now the third case, I have only one force acting in this direction, which is trying to rotate it in the anti-clockwise direction. The distance is R, so the torque is Rf and the total force is F. So these are the three different cases. You can have torque with 0 force, you can have force with 0 torque also. So these conditions are possible. Torque is also related to the rate of change of angular momentum. Let us see how it is related. Angular momentum is L. Rate of change of angular momentum is d by dt of L or dl by dt. I'm going to substitute for angular momentum L as r cross p. So it will be d by dt of r cross p. This is equal to dr by dt cross p plus r cross dp by dt, because it is uv form, d by dt of uv form. You have studied differentiation. Now you look at dr by dt in cross p. P is mv. dr by dt is velocity v. So v cross mv you are getting. V and mv are parallel. So they will become equal to 0. M is a constant, you can take outside. So m into v cross v you get. So this will be equal to 0. So this term will not be contributing. And dp by dt, rate of change of momentum, is the force acting F. So you can substitute F for dp by dt. So finally you get dl by dt is equal to r cross F. And what is our r cross F? That is our torque tau. Therefore torque tau is equal to dl by dt, or torque tau is equal to rate of change of angular momentum. Now what will happen if the torque is 0? If torque is 0, rate of change is 0. Rate of change of angular momentum is 0. Rate of change is 0 means it is remaining constant, it is not changing. So when the torque is 0, angular momentum L is a constant. That means angular momentum is conserved.